I would like to welcome everyone to this presentation on enhanced rockfall analysis using RocFall2 and RocFall3. My name is Grace Huang, and I'm the products manager for RocFall2 and RocFall3, and I will be the presenter for today. So the agenda, I will start off with a brief introduction to the company. I will then explain what is meant by statistical simulation of rockfalls, which is used in RocFall2 and RocFall3. Followed by an explanation of the benefits of conducting 2D and 3D rockfall analysis. I will also go into more detail of the physics and impact theories behind RocFall3, which was recently released last year. Now, for the second part of the presentation, I will do a demo that shows some of the latest features in both programs, as well as the integrations between the 2D and 3D software. So to get started, let me introduce Rocscience. Our headquarters is based in downtown Toronto, and our primary business is to develop and maintain geotechnical analysis software for civil and mining engineers. We currently maintain a list of 18 products to meet the various needs in your geotechnical and mining projects. The software can be broadly categorized for analysis in slope stability, excavation and foundations, and settlement. Among these, we have RocFall2 and RocFall3 for the statistical simulations of rockfalls in 2D and 3D respectively. So let me explain what is meant by statistical simulation of rockfalls. The statistical approach is effective for overcoming the challenges associated with accurate prediction, because we know that rockfalls can be affected by many different factors, including the variations in slope geometry, initial conditions of the rock, the slope material properties, as well as the rock attributes. Unfortunately, these are all factors with high uncertainty and difficulty in testing. And coupled with the sensitivity to these parameters in modeling, the accurate prediction of rockfalls is practically impossible. So we do statistical simulations instead, where we assign statistical distributions to slope and rock properties and initial conditions. Then we randomly sample sample the parameters in each simulation, and we can conduct many simulations. So we throw hundreds or thousands of rocks down the slope to get a reasonable distribution of the rock and locations, downsides, and energies, which are quantities important to design. So rockfalls can be analyzed in either 2D or 3D, and there are advantages to both of their applications. So probably a number of you are more familiar with rockfall simulations in 2D, such as in RocFall2. 2D simulations are typically very fast, so they're very suitable for computing the large number of simulations required for statistical or sensitivity analysis. So as an example, in this figure, I am showing you the RocFall2 barrier sensitivity analysis, which is intended to help with barrier design. So here the barriers are shown by the red and blue lines. The user can vary the barrier location along the slope, as well as the barrier inclination at each location. And so that the energies and downsides can then be examined for different combinations of barrier design. The outcome can then be visualized in a 3D histogram with the location and inclination of the barriers on the two horizontal axes and the rock energy on the vertical axis. Now, the benefit of 3D simulation is that it can account for the 3D nature of the slope geometry and rock trajectories. So we know that rockfalls are typically never confined to a 2D plane. The 3D analysis can also provide insight into the rock runout distances as well as the lateral extents, which in 3D can be visualized as a heat map of the rock and locations, as shown on the right here. The 3D simulations can also be used to identify critical slope sections, which overcomes the challenge of slope geometry definition in 2D. Then these critical cross-sections that are identified in 3D can then be exported to 2D for more extensive statistical or sensitivity analyses. Or multiple sections can be exported to 2D to compare rockfall hazard among these sections. So because there are advantages to either the 2D or 3D analysis, RocFall2 and RocFall3 were designed to work together. And later in the demo, I will show some of the integrations. So now for the physics behind a 3D rockfall simulation. As mentioned, RocFall3 was recently released last year, and our upcoming release, our update, provides an expanded rock shape library for the rigid body analysis. So I would like to spend some time discussing the details behind the 3D physics engine. So a rockfall trajectory can be broadly categorized into projectile, impact, sliding, and or rolling. So the events for projectile and sliding and rolling follow basic laws of motion, whereas impacts are an ongoing topic of research, which I will get into a bit more. The impact theories behind RocFall3 are lump mass and rigid body. In lump mass, the rocks are modeled as particles without shape, and in rigid body, the rock shapes are explicitly modeled. And the 3D rock shape library includes regular polyhedra as well as extruded polygons. Both theories utilize the coefficients of restitution, and I will explain in a moment as I go into each theory. Now, for those interested, I have provided here a list of references that are used for the rigid body engine. So the lump mass impact theory is the same in 2D and 3D, except in 3D we have to consider an additional tangential direction. So before impact, the incoming translational velocity is resolved into one normal component and two tangential components. The coefficients of restitution are then applied in the respective directions as sources of damping. These coefficients range from 1 to 0, 1 to represent a perfectly elastic impact with no damping or energy loss, and 0 to model an impact with full damping and complete energy loss. The lump mass impact theory also accounts for rotation, but we have to make some assumptions. We know that rocks with shape can rotate, but in the lump mass theory, rocks are modeled as points without shape and without moment arms, so they cannot practically rotate. This is why we require user inputs for rock density and mass so that an equivalent volume and radius can be assumed for calculating the rotational velocity. Another assumption is that in order to ensure the conservation of energy, a relationship must be established between the rotational and tangential velocities, as shown here in this formulation from Pfeiffer and Bow in 1989. The 3D rigid body impact theory incorporates elements of non-smooth dynamics, where impacts consist of sudden jumps or discontinuities in motion. The rigid bodies are represented by closed triangular mesh volumes, like the one shown here. And as rigid bodies, they cannot deform. There could be multiple contact points, meaning that impacts can be influenced by multiple materials. And damping is applied at these contact points through the coefficient of normal restitution and dynamic friction. The impacts also satisfy constraints in non-penetration, energy conservation, and symmetry preservation. The last one simply means that any symmetry entering an impact is preserved with symmetry exiting an impact. Here, I'm showing the impact calculation sequence for rigid bodies. So before an impact, we have generalized velocities calculated at the rock center of mass. And generalized velocities consist of both translational and rotational components. Now, with impact, the generalized center of mass velocities are then mapped to all contact points. And these incoming contact velocities are resolved into a normal and tangential components. And these are translational velocities only at the contact points. Now, to get the outbound velocities, we apply the coefficient of normal restitution to the normal velocity component, and the friction is applied as an impulse acting opposite to the incoming tangential velocities. And with multiple contacts, you can have different sets of restitution and friction applied at each contact point depending on the material in contact. Now, the outbound contact point velocities are then mapped back to the center of mass as generalized velocities as the rock enters its next phase in the trajectory. So sliding and rolling are accounted for separately from impacts. In the lump mass theory, the formulation is the same in 2D and 3D, where the translational velocity is reduced as a result of friction. So here, the friction angle is the key parameter. However, an assumption has to be made in that without a moment arm in the particles, only the translational velocity is reduced and the angular velocity remains unchanged. The rigid body sliding calculation uses a planar friction model or a friction cone that obeys the isotropic Coulomb friction law. This means that the same dynamic frictional property is applied in every direction on a plane, and the frictional impulse is coupled to the normal impulse. So when the rigid body is sliding, the frictional impulse is exactly equal to the dynamic friction mu times the normal impulse. So to handle multiple simultaneous impact at different contact points, we are using a linear complementarity formulation. So this means that our friction cone also has to be linearized as an approximation. So I'm going to do a demo in RocFall2 and RocFall3 for the second part of the presentation. I will show two examples where the two programs can be used together and some of the new features in each program. So in this first example, I'm going to start in RocFall2, and then I'm going to import this 2D file into RocFall3 to show how you can use 3D analysis to supplement the 2D analysis. So in the slope in RocFall2, you can see 3 different materials as shown by the different colors. This crosshair here is a poinsettia used to designate the source of rockfall. Let's go to project settings and let's use rigid body analysis. Let's take a look at our materials again. So you can see for each of the materials, a statistical distribution has been applied to the restitution values. Now for the cedars, let's change the number of rocks and define the rock shapes. So for this example, let's use 100 rocks. And shapes, we can use, let's say, polygons. And I'm also going to enter some statistics for the rock mass. You can also see that the cedar has some initial horizontal velocity with a distribution. Okay. So let's compute. So you can see that just by entering statistics to the slope material parameters and cedar properties, you get a distribution of the rockfall trajectories. We can then very quickly plot runout distances. So graph endpoints, runout distances. In 10 bins, I get this histogram of the runouts. So now let's try importing this into RocFall3. You may consider importing a RocFall2 file for 3D analysis when the sectional geometry is fairly consistent in the longitudinal direction, but the RocFall source geometry or slope material assignments are better defined through 3D modeling. So as an example, let's assume that the slope geometry is almost the same for 50 meters. So we can extrude it by 50 meters in 3D. We can also import the poinsettia that was in 2D into 3D as a line cedar and specify a cedar extrusion depth. So let's use 10 meters for that. So the model extent is 50 meters. This line cedar here is 10 meters. You can also see that the 3 different materials have been imported. Let's take a look at the rock shape library. So you can see that the polygons from 2D have also been brought into 3D. But the 3D rock shape library also has its own fully 3D shapes or the regular polyhedra. So these are, for example, the icosphere, tetrahedron, dihedron, dodecahedron, etc. But for now, we'll use the same extruded polygons as the 2D analysis. In 3D, we can incorporate the 3D effects in cedars and materials. So for example, for this cedar, let's add a distribution to the orientation of its initial velocity. It currently has a trend of 90 degrees, and trend here means the clockwise from the y-axis. So let's use 90 as the mean, give it a normal distribution, a standard deviation of, let's say, 15 degrees with a relative min and max. We will also randomize the initial rotation of the rocks, so then they can now fully rotate in 3D. Let's now introduce 3D effects to the material regions. You're seeing the slope now from a top-down view. To define material regions, you can draw them in polygons. Cute. So now in 3D, you can visualize not only the runouts, but also the horizontal spread of the rocks. So we know that the cedar is 10 meters. So let me annotate that. We can see that the spread of the rocks be about 15 meters. You can also visualize the endpoint distribution on a heat map. So for instance, I go to surface, histogram of the end. And then you can use this information to help you design your barriers. And so let me just quickly do that now. Define some barrier properties. You can have a custom barrier model with either an infinite capacity or a user-defined capacity. But we also provide a barrier manufacturer library, so you can access barrier specifications from 5 different manufacturers. We just quickly add a barrier. So in 3D, you can add the barrier in any orientation in this full 3D space. And let's recompute again. And let's try plotting some barriers. We can have a histogram of the energies, velocities. Well, let's try bounce height for this example. So here you have a histogram of the bounce heights on the barrier. Now, one last feature for this rigid body example is the animation with actual size that I would like to show. Let me go to options. I want to view the rocks in actual size. And all the rocks at the same time. Okay. So this concludes example 1. For my example 2, I want to show when it is useful to start with the 3D analysis and then enhance it with 2D analysis. So for this example, I am going to use the lump mass impact theory. And for the geometry, I'm going to bring in a DEM from our terrain generator. So here we can access satellite data to most parts of the world. You can specify the location and the extent. So I'm just entering some coordinates. West coast of the US. I want a region that's about 0.5 kilometer by 0.5 kilometer. I also want to bring in the surface texture, which is the image, onto my model. Let's go to post-processing. So whether you are bringing a DEM or you're using your own point cloud or .obj.dxf, whatever geometry file, it's always a good idea to check the triangle count to see just how large your model is and to simplify it as necessary. So if you have a 32 gigabyte RAM, you can handle 30,000 triangles on the surface just fine. It's also recommended to make sure that your surface is watertight, and this is critical for 3D Rockfall analysis. And we offer geometry find and repair tools. So my model doesn't have any geometry defects, which is good. So let's bring in the texture and click done. So the terrain generator is a very useful feature for bringing in the natural geometry that may be bounding your infrastructure. And you can also use it for large scale Rockfall analysis as well. So in this model, I'm going to define 4 materials, the bedrock outcrop, the asphalt for the road, soil with vegetation, and the water. So let's define these. So you can see for material properties in lump mass analysis, the parameters used are the restitution values and the friction angle. Okay? And you can define a statistical distribution for each. Let's change the name to soil with vegetation. And let's add one more material for the water. Now, for the parameter values, a good starting place is to check the materials library where we have provided reference values. To use a default for the bedrock. For the soil, I'm going to use a smaller restitution value for greater dampening. Default value for the asphalt. And for the water, I'm going to use 0 for all the restitution values and 90 for the friction angle so that the rocks can be completely stopped when they come into contact with the water. So now we want to assign these materials to the slope. In our first example, I did that by drawing material regions or these polygons. Another way to assign materials is through our image segmentation tool. Okay, so here you can see the original surface texture image on the right and the processed segmented image on the left. It's currently using 4 segmentations, and the colors you're seeing are the average of the original image color. But you can also visualize it in terms of high contrast colors or assign material colors. So one way to utilize the image segmentation is to just bring in your own original image with high contrast, which is what I'm going to do. So geometry, I'm going to assign a new texture to the slope surface. And I'm going to do image segmentation on this high contrast image. I will show you segment the image in assign material colors. So this is the soil with vegetation. This region is the water, and this is the road. So the image segmentation tool can quickly help you assign materials to your slope based on an image. Let me turn on topographic lines for easier viewing of the terrain elevations. I'm just going to make it less dense for easier viewing. Okay. Now for this example, let's assume we want to know what happens if the rock falls are coming from an elevation of 150. So we can define a line seeder at the elevation of 150 with some statistical properties. Let's just use default values, but I'm going to increase the number of rocks to, let's say, 200. Seeder. Slope. So I drew a line seeder following the topography. Cute. You can quickly see that the rockfall hazard may be more critical near this side of the highway where my mouse is. But you can also see that rockfalls tend towards valleys, like the one here. Let's view the endpoints on a heat map. So you can see that the 3D analysis has helped to identify critical slope sections. We can now export these critical sections to 2D, where you can then perform an enhanced statistical or sensitivity analysis. But before exporting these sections, I want to define a reference line. So this reference line can be used for calculating runout distances. And it can also be exported to 2D and used as a reference line across multiple slope sections that are batch exported. So I'm drawing this reference line at the side of the road here. Let's look at the runout. So this is a histogram of the runout distances with respect to the reference line. Now let's create some sections for export. We can either create a single section or multiple sections. But we could consider using both for this example. So for instance, I may want to create a single section that follows the valley, where we see rock falls going towards. You can also create multiple sections in the high risk area for further examination. So you can do this by drawing a line segment and defining the number of sections that cut through this line, or you can specify the distance between the sections. For instance, I want a section every 20 meters. So in this example, I'm just going to have 3 sections cutting across a line that I draw. So we have created our sections. Now let's batch export these. Now I want to, let's say, compare the hazard for the 3 sections from the high hazard area. So I can batch export these 3 sections along with the reference polyline and any cedars that are also in that area. So the sections have been brought into RocFall2. You can see that this crosshair here was the line cedar in 3D. Now it's a point cedar in 2D. And this dashed line is the reference line. Now to compute, let me first simplify the slope geometry. Let's quickly do a batch compute for all 3 sections. Okay, so the trajectories are quite light. As these sections were batch exported, we can do a group analysis in 2D. So for instance, if I graph a group plot, I can find the runout distance either from the rock starting point, the cedar, or from the reference polyline that I exported. So now in this group plot, you can see the runout distances from all 3 sections in one place. And this is useful when you're trying to compare across different sections. Now, you can also you can also export a 2D section to conduct a more extensive statistical analysis. So for example, for the section that cuts through the valley, okay, do a rigid body analysis on this. So for the statistical analysis in 2D, you can try to either increase the sample size to get a more reasonable distribution, or you can also vary the slope geometry at the vertices. And this may be useful if your 3D DM does not offer the resolution that you want. And keep in mind that the resolution of the terrain generator does depend on the location and the availability of satellite data. So to vary the slope location, I can go to slope, edit coordinates, and then give the X and Y coordinates some standard deviation. Let's just compute. Now, one other thing that you can do when you bring the model into 2D, you can also study the effects of force damping if you think that may have an impact on the trajectories. So this is a model with variations in the slope vertices. These dark gray lines are just the slope geometry variations. Now, if you wanted to look at force damping, you would have to go into the slope material library and enter a damping coefficient, for example. And these are just a couple of examples of the statistical capabilities of RocFall2. So this concludes my demo, and now I'm open to any questions that are unanswered in the chat. Is it possible to import a civil 3D surface into RocFall3? How do you do it, and what features should this surface have? It depends on what format you are importing from in civil 3D. So for instance, we do support, let's say, Autodesk files or .dxf. The full list is on our website. If Ellen, if you could direct them to that page, that would be great. Thank you. Sometimes using the rigid body method, the particle tends to jump more than with the lump mass method. Is there any way to improve this? One way is in both 2D and 3D. Sorry, let me just go to 3D for a second. For rigid body analysis, you also have the option to scale the Rn by either velocity or by mass. So these scaling factors basically account for the fact that during an impact, there is deformation on the slope and in the rock that is dependent on the velocity or the mass of the rock, and the Rn is then scaled accordingly. We recently purchased RocFall3, but for the rigid body analysis, the option for different shapes is disabled, and it can only show the sphere. Yeah, so for versions 1.005 and earlier, the rigid body was for sphere. But with our upcoming release scheduled for next week, you will have access to the full 3D library that includes the regular polyhedra and extruded polygons. Can we import the geometry of the hazard rock if we have a 3D scan? Yeah, that's a very interesting point. We currently cannot, as we're just using predefined shapes. But if this is something that is in high demand and people find a lot of value in it, that's absolutely a feature we can consider. Great background demos. Would you please talk about the dynamics of bodies that break apart, changing direction upon impact? Okay, so currently we do not have rock fragmentation in our analysis. We simply assume that the rock mass and volume are constant throughout its trajectory. Of course, people are interested in rock fragmentation because it is a source of energy dissipation. And as a result of this additional dissipation, the runout distances may not be as far as you would get without the fragmentation. So that is something we are looking into, but it's not something we are supporting currently. Also, is there a quick way to import coordinates for barrier and cedars? If you click on the cedar properties or geometries, you can paste in coordinates. Can we estimate the maximum impact? So if by maximum impact you're referring to the energy on the barriers, or let's say the maximum bounce height on the barriers, you can either do that by plotting the barriers, or we have this, sorry, so it's either by plotting, or you can view information of the trajectories in this rock information table. And you can sort the path by energy or velocity or runout distance, etc. And you can sort it by just clicking on the header. And this table offers filtering options for the path as well. So for instance, you can see the stopping reasons. Did they stop, or did they hit the barrier, or did it reach, let's say, max compute time? I think you're asking why you may want to put the rock above the slope rather than exactly on the slope. This is to ensure that there's no penetration into the slope as being one of the reasons. Can we define the barrier height in Rockfall2? Yes, you can. So for instance, if I'm just adding a barrier here, you can specify the height as well as the inclination. So Maha has a question. It only takes it cell by cell. It does not copy a whole table. If you are wondering how you can export data, there are ways. So for instance, this rock information table here can be exported to CSV. Now, if you want the trajectory information, so if you want the velocity with time or position with time, with energy with time, etc., you will need to go to File, Export, and then Export All Results. That's how you get more details on the trajectory. Do you estimate the impact force, not the impact energy? the impulses from impacts are calculated based on the coefficient of restitutions and friction. Will we receive a copy of this webinar? I believe that we post our webinars on our YouTube channel, and Sayana, please correct me if I'm wrong on this. And also, we will compile a list of the responses to your questions and email them out in the following weeks. If the slopes are covered with colluvium and scree, how reliable the results would be? Yeah, I agree. You would have to enter statistical distributions for your material parameters to study its effect on the distribution of the rock endpoints. To determine the initial velocity. Sometimes people have field data if they're using some sort of instrumentation. So that's one way to approximate it. But if you don't know, you can start with 0 and maybe put in a mean value and apply a distribution to that initial velocity, which will create a spread in your rockfall runouts and end distributions. Is there any other way to define the coefficient of restitution other than the default setting? Okay, so for the coefficients of restitution, as mentioned, a good starting place for the parameter values are the material library comment types, which provides you with some mean value and a standard deviation. Now, if you wanted to do back analysis, you would need field data. And you would need to, so for instance, you would need to know at least where the rocks are ending or where they are impacting on the slope. And if you have some sort of instrumentation to record historical rockfall events, that can help you with the back analysis. So I would first start with just, having a rock bounce normal to, let's say, the ground to see its rebound height. From that, you can back calculate the normal coefficient of restitution. And then for the rest of the trajectory in rigid body analysis, you would then have to calibrate the friction angle. Can the trees be considered in the future in more detail? Yeah, as Ellen responded in the chat, RocFall2 has forest damping. It's not in RocFall3 at the moment. We are considering it as a future feature. Could you please consider supporting Mac OS, not just Windows? Noted. We will take back your comments to the team. I can see that fragmentation has come up quite often as a question, and people also ask me this at other venues as well. It is something we are considering seriously, but really we need a way to incorporate it into our statistics that we currently have. Okay, one more question. What are the maps available? How to know if my region is covered? I guess as an FYI, our terrain generator is provided by a third-party software called Mapbox. And at least according to their website, their data does vary by, their satellite availability does vary by location. We found that at least in the US and Canada, the resolution has been okay. Can send you the details on the resolution in our follow-up email. Now, for other parts of the world, what you can do is if you try out RocFall3, and we do offer a 14-day trial, try the terrain generator for your region to see how it is. It will be interesting to be able to import image in RocFall 2D as we can do with slide to design a section. Yeah, so we can export 2D sections from 3D into 2D to help you with your design and analysis. Because 2D will be, so 2D, you can probably use a larger sample size. You can vary the slope geometry, put in forest damping to enhance your statistical analysis to get a better distribution. Can I get my region map from Google Earth? So right now we don't use our map from Google Earth. You may be able to get a surface texture like a satellite image from Google Earth, and then bring that into RocFall3 to project it onto the slope geometry. Okay, so this is the end of the webinar. I would like to thank everyone for your attention and all of your great questions. And please be assured that we will follow up with a list of responses to your questions. And if you have suggestions for future webinar topics, please let us know. Thank you very much, everyone. Have a great day.